Alright, let's take a look at exercise 1.2. We have the quadratic equation z squared plus bz plus c has roots alpha and beta. And then we're told that alpha plus beta is equal to 4, and alpha squared plus beta squared is equal to 8.5. Find the values of b and c. Alright, so alpha plus beta equals 4, and we know that if we have az squared plus bz plus c equals 0, from Vieta's formulae we know that negative b divided by a is equal to the two roots added together, alpha plus beta, and c divided by a is equal to the two roots being multiplied together. So, since a equals 1 in this case, we immediately have that negative b is equal to 4. So that would mean that b is equal to negative 4. Now, how do we go about getting c? In this section of further maths, they use a lot of little tricks like this. We can see that alpha squared plus beta squared, alpha squared plus beta squared is actually the same as alpha plus beta squared minus 2 times alpha beta. Now the thing we're actually looking for is alpha beta, since we know that alpha squared plus beta squared is 8.5, and we know that alpha plus beta is 4, so alpha plus beta squared is 16, minus 2 times alpha beta, the thing we're looking for. Okay, so rearranging this equation, we get to alpha beta is equal to 7.5, or 15 over 2. And so that means that alpha beta is equal to 15 over 4, and that is equal to c divided by a, and a is 1 in this case, so c is equal to 15 over 4. And then we're done. Okay, exercise 1.3. The roots of the quadratic equation z squared plus 5z minus 2 equals 0 are alpha and beta. And so immediately we get that alpha plus beta is equal to negative 5, and alpha times beta is equal to negative 2. So obviously we could find alpha and beta if we wanted to, and then just find 1 over alpha and 1 over beta and go from there. But it says by making use of a suitable substitution. And this is a technique that we're going to come back to multiple times with polynomials of degree 3 and degree 4. So we may as well introduce it here for the easier case of degree 2. Now, the idea is pretty much as follows. If p of alpha equals 0, which would mean alpha is a root of this equation here. So we're calling, p of x, p of z. So we're calling this polynomial here p of z, and we're setting it equal to 0, and we're saying alpha is a solution of that. Then so long as alpha does not equal 0, p of 1 divided by 1 divided by alpha should also equal 0. And the exact same thing with beta. So p of beta equals 0, beta does not equal 0, then p of 1 divided by beta equals 0. And then from there we can make the simple observation that p of 1 divided by, and then you can just choose another letter. The book usually uses y. So p of 1 divided by y equals 0 has solutions y equals 1 divided by alpha or 1 divided by beta. And then from there, just observe that p of 1 divided by y is also a polynomial. So p of 1 divided by y is equal to 1 divided by y squared plus 5 times 1 divided by y minus 2. And then, well, I'm sorry, it itself is not a polynomial, but when we set it equal to 0, we can get an equation with a polynomial equal to 0. That's what I meant to say. Don't hold me too responsible. So 1 divided by y squared plus 5 divided by y minus 2 equals 0. And then because both sides are equal to 0, we can of course multiply both sides by y squared. And so we get minus 2y squared plus 5y plus 1 equals 0. And since these two equations are equivalent to one another and they both have solutions, y equals 1 divided by alpha, 1 divided by beta, we have found the equation of a polynomial equal to 0 with roots 1 divided by alpha and 1 divided by beta.